Hello. Um, I also gave a presentation yesterday touching on some of the things that I'm also going to talk about today. I hope I'm not going to disappoint. I mean, how many things can you end up to talk about in a presentation? But this presentation is about the project we've been working on and some of the lessons we've learned most the hard way. So what I've been working on is a project at E.On that handles monitoring and controlling of power plants. Of course, we are not talking about nuclear power plants. We are talking about small power plants, like based on biogas or wind farms or stuff like that. You know, in the green energy department. The project is based on microservices, and it's about processing of signals in real time. We read signals from multiple input sources and inferring state from that, and depending on their state, possibly controlling those plants, sending them, commands. In principle, we are talking about dispatching flexibility, make them produce more. Of course, I'm talking about soft real time. We don't have like real time requirements, actual real time requirements, but we do have not so generous service level agreements about resilience and response time. And the whole system feels much like an orchestra playing a symphony with many parts that communicate with each other. It's kind of overwhelming at times. But yeah, real time as a sort of definition is about systems that receive inputs describing the state of the world and reacting in real time to that input, changing the environment, sending commands, declaring faults, triggering alarms, and so on. And on top of the JVM, this implies asynchrony, my favorite subject, because you often receive input from multiple sources at different times, and you have to merge those input sources, you have to combine them, and this really implies non-determinism and concurrency, the things that keep me awake at night. And when dealing with the synchrony, it's not something that you can fix later. You have to design for it. Of course, that doesn't necessarily mean fancy solutions. I'm not talking about scaling and using special solutions or anything, but you really need to plan for asynchrony. This has to be baked in your design from the beginning. So let's talk a little about Akka actors. Between my acquaintances and the projects I've been working on, Akka actors are fairly popular. I've come to consider Akka actors as sort of a standard solution in the Scala community because of their popularity. They have good parts. They provide proper encapsulation by most standards. I mean, for stateful things, they do have encapsulation. They've got concurrency guarantees, meaning that messages are processed in order, and this helps. And message passing can be over address spaces, so you can communicate with actors in the same process, the same as you would with actors that are over the network. It doesn't make a difference where an actor is, and they've got supervision being built on the let it crash mentality, and that's good, because in distributed system, problems happen. And there are also bad parts to them. There are no common best practices. There's a new book on Manning, I think wrote by Dr. Knuth, but it's a new book, and the best practices that we know are probably coming from Erlang, and we don't really know Erlang. And the solution is too flexible. I mean, actors, that's the signature of actors of their receive method, any unit. And this really describes actors. You can see how flexible they are. I'm not going to complain that they are untyped. I think there are good reasons for why actors are untyped, because actors usually describe state machines, and there's not much use in saying, what the whole set of messages that an actor responds to, because actors are state machines and asynchronous. It's more relevant what messages they respond to right now versus the whole set. This is how I feel anyway. And because they are flexible, they can do bidirectional communications. Actors can have dialogues. They can do ping-pongs. And this leads to cycles in your communication graph. And cycles in your communication graph represent the depth of your system, because things get so complex if you end up with cycles. When speaking of actors and distributed systems and concurrency can't happen only when speaking of variables in memory. It's not only about protecting memory location. It's also about concurrency in your communication protocol. And we ended up with concurrency problems in our communication protocol because we ended up with multiple sources of truth for the same thing, and different things can end up happening in different components in your system and then ending up in a conflict with each other. It's hard to describe, but it happens. It's really not about synchronizing memory when it comes to concurrency. It's also about communication. It's all about communication, actually. And because they are stateful and asynchronous, the problems that you can have with actors are actually worse than the worst you've ever seen with OOP and stateful things. Because actors can evolve by themselves with no input from the outside world. And before you say that you are not using Akka actors, all problems of actors are problems of microservices and distributed systems. And talking about some things that we've learned and we've been bored with. This is an anti-pattern. Usually, this is something easy to do. You set a tick that is getting triggered every 3 seconds, and you evolve the actor in some way, do a request, a database request maybe, and you do stuff. This is an anti-pattern because it's hard to test. All messages should be external. The actor should only evolve in response to external messages, because otherwise this is untestable. Of course, for throwaway code or things that are not important, you can of course do this, but actors should only evolve in response to external messages. And another anti-pattern that happens by accident mostly is exposing the external state. Actors protect us. They've got encapsulation. We have some ordering guarantees. Messages are processed in order and so on, but you can easily expose your internal state in closures. This for loop is a for each on a future, and readings escapes and will be processed in another thread, which is not going to be in the context of our actor, and this will lead to multi-threading issues. This is an accident that can and does happen because actors are used in combinations with futures. And instead of Doing that, and also instead of blocking on the results of futures from inside the vectors, what you usually should do is to model a state machine, of course. So we, in this example, initiates a future whose result is going to be piped to our actor when finished, and then we evolve in a state that waits for that response. And in this state, we can do specific things, like we can ignore further ticks or other messages, and then we go back to receive when the future is done. This is like the usual way to work with vectors. This is how people would do it in Erlang. You do something, you evolve in a different state that will process different messages, and then you evolve back. Evolutions and context become, I hate variables and mutable data structures. And the way to work with vectors, the way how Erlang does it, is to evolve the receive function. And we can also do that with Akka. Instead of having a state that is mutable, we can have special receive functions, and we can evolve them with context become. So in this example, readings is no longer mutable. It's passed as an argument to our receive function, and we simply evolve it when we've got a new state. This works, and it protects you from problems like if you capture readings in a future, at least you won't be able to modify it. It's going to be read-only because immutable. Okay. So, of course, it's a pretty bad idea to place input-output logic in actors. Input-output logic should be outside of actors because actors are hard to test. Actors should be used for aggregating and for inferring state, but I/O logic should be placed outside, and whatever readings you're doing should be pushed as messages to that actor. The actors should stay minimal. And one big problem that happened is that we often talk about effects that our code does to the outside world, but sometimes we are talking about input provided by the outside world. And one such example is date time now. So we can have code that depends on time, on date time now. In case we are doing a reading in a sensor of a power plant, we are going to attach a timestamp to it because information loses value the older it is. So if it's fresh, then you can use it. If it's old, then you discard it. This is an example. You want to attach things to your data, right? You want to attach time stamps. But sprinkling date time now all over the place means that your input is going to be implicit, and this introduces non-determinism, things that are hard to test. Okay? So what we do is to make everything explicit. So no date time now anywhere. Everything is passed as an explicit argument. Including timestamps. And speaking of purity, I'm going to talk about how we handle state and effects. I believe Chris kind of talked about earlier about some of the things that I'm going to talk about today. I'm going to show you what a working Java developer would end up with. We are not using the state monad. We might use the state monad. Right now, we are doing something like this. So first of all, we model state machines in a pure way with pure data structures and pure functions evolving those data structures. This is just a simple example. In case we receive a message, we evolve the state machine. But this is not enough because I'm evolving a data structure. doesn't describe anything that we need to do. When speaking of dealing with purely functional state, there are two patterns, actually. So one would be having a function that takes the current state and an update message and will evolve it to a new state. The other one would be taking the current state and producing some side effects along with the new state. Astute readers will recognize this as being, the signature of the state monad. It's a useful signature to keep in mind, and we can use both in this example, because we can model side effects in a pure way as a description, as a specification. In this case, we might have side effects like status updates of a power plant. We can have like a signal of a transition that happened from available to a fault. We can have a dispatch that represents a command sent to the power plant. Or we can have, an alert that happened in response to a would-be fault that isn't declared yet, but, somebody might do something about it. And when modeling the data structure, we can have two things. We can worry about two things: evolving the state machine and producing side effects. Evolving the state machine can trigger side effects specified purely as output, but we keep it internal until we really need it. This is, the state function. And when we need it, we extract it from our state machine and do something with it. We materialize it. This is materialization of the effects. I'm not sure if I'm using the right terms, by the way. And the actor can become something that deals only with communication at this point. The actor can do context become on our state machine. On receiving an input, it will simply evolve that pure data structure that we've just built. And when receiving a produced tick, let's say, it can pull out the required side effects specification and push them into a global channel where they can be processed. I'll talk about this channel later. So we are doing a complete decoupling here. We no longer have to test this actor because this actor becomes a standard actor. We no longer need Akka test kit, okay? We can just test the pure data structure and the pure functions. Of course, at this point, I think I'm preaching to the choir at this conference, but this is my mascot for this presentation. Talking a little about the architecture. The main component that I've been involved with looks something like this. So it handles controlling and monitoring individual power plants, and the process can handle multiple power plants at once. There is a supervisor that reads configuration from the database and transforms that into a stream of updates, because people can come in and update, like they can add new configurations, they can remove configurations, they can update the existing ones. And according to these configurations, we create state machines that model the behavior of power plants. Of course, the configurations determine their behavior in the database. So the supervisor reads configurations and starts and stops sectors. When a configuration changes, it's easier to just kill an actor and start it over instead of worrying about, mutating its state safely. And actors receive input from multiple sources, like from their sensors or from components that trigger commands. And we have outputs that I just described. It's specification of output, it's pure. And that output gets thrown into a queue of messages, which is going to be a global queue of everything that happens in this system. And we can pull that from that queue and do persistence in time series. Again, complete decoupling. We don't have to sprinkle the code with database persistence, for example. Database persistence is not the purpose of the state machines. We can, trigger alert signaling to, we can send emails or whatever when problems happen. We can send commands through SCADA, which is like this protocol used in the industry. And this is like opinionated philosophy. I'm a man of strong opinions, sorry. I think that whenever in the code base you see mocks and stubs, I think that's a sign of tight coupling. We do not use mocks and stubs. We do not need to do that. And also data dependency injection techniques that are used for hiding the problems you have in your code. I think GWIS and the cake pattern and whatever, anything except plain old constructor injection is bad because it's used for hiding problems. If a component you have has too many dependencies, that's a problem. It's not a problem of injection, it's a problem that you have too many dependencies. And I believe in pain-driven development. I don't believe in hiding things. So So this is another one of my favorite subjects, usually because it sounds cool. But when dealing with communications between producers and consumers, we can have the problem that the producer might be too fast for the consumer to consume. The consumer might be too slow. It might be expressing problems. We might talk about an open TSDB that's slow and crashes and discards our data. Well, we all have heard stories of problematic databases. I think this is like a rite of passing for any software developer to have problems with his database. And in a distributed systems, things can happen. Networking can go down. VMware can steal your CPU resources, and any unlimited queue of messages that you have in your system can blow up, can blow your process up because you will be at some point out of memory. This is one problem that happened in our system. So because we had a cron job set to run every 15 minutes in combination with certain conditions that led to this cron job use extra resources in the morning, this script was using so many resources that VMware was pulling resources from other instances, and so those instances were remaining without CPU power, CPU capacity, which led to networking issues, which led to failed requests to OpenTSDB, which led to queues being filled up with unprocessed messages, which ultimately led to crashed processes. And in a distributed system, you have to prepare and make your components as resilient as possible. If you can have unlimited queues in your system, that's a problem. And what back pressure means is ideally you can pause the producer of data. If you keep doing repeated HTTP requests, of course you can make less HTTP requests. You can adjust the rate. Or in case you cannot control the producer, which happens, you need an overflow strategy. What happens when your buffer is filled up? So you can have a limited buffer, and when that buffer fills up, you can choose to drop events on the floor. It's healthier than having crashed processes. And in case you drop events on the floor, you can be redundant. I mean, why send a single message when you can send many to do something, when you can repeat the message like continuously? Oh shit. 5 minutes left, okay. Monix is, I described Monix earlier, yesterday. And it's evolved in parallel with this project, and it's a modular project. It doesn't have third-party dependencies right now. Minitest is used for testing. Synchron is a sub-project that deals with really low-level stuff. Currently, it deals with atomic references, doing I'm not going to describe that. Monix execution dealing with scheduler and cancelable, Monix eval dealing with task, what I described yesterday, and Monix reactive dealing with observable. Observable, Runar is my Scala hero. He said in one of his presentations that a constraint at one level gives us freedom and power at a higher level. Actors are simply too flexible. And observable is all about unidirectional streaming of events. It's about asynchronous streaming of events, of course. With observable, you model a communication between one producer and one or many consumers. It handles back pressure by default, baked in the protocol. You can handle back pressure with back actors, but you have to implement that protocol yourself. And it's composable. If we are to describe observable in relation to things we know, if a function is something that produces a single result and future and task produces a single asynchronous result, and iterable is something that produces synchronous multiple results, then observable is the equivalent of iterable, just asynchronous. By the way, a task or a future can be seen as an observable that produces a single element, and the comparison is actually quite useful. As a quick sample, we can convert any iterable to an observable, and we can do filter and map and flat map on it, of course. Any self-respecting thing can do flat map. And we can subscribe to it. I mean, until we subscribe to it, nothing happens, so an observable is a description, it's a specification. Subscribe is something that can happen at the end of the world for doing side effects, for consuming the stream. Subscribe is about consumption. It needs a scheduler, of course, just like the Monix task. And we can be like more specific what happens on subscribe. We can specify callbacks that happen for each element. And here we can do the side effects. Here we can make OpenTSDB requests that can fail. But we can simply print elements. There's actually quite a parallel between observable and task. We've got all the nice constructors like now and eval always, which is the equivalent of a function, eval once being lazy val, defer, fork, and from future. We can convert any iterable or any reactive publisher meant for interoperability. Yeah. We can repeat an evaluation indefinitely, like we can generate random numbers. Of course, we can do from state action and generate random numbers like the cool kids are doing it in a stateless way, We can repeat, we can generate ticks at certain intervals, and now you can think back to when I said that we should externalize these ticks. I mean, observable can do it, I'm saying. And we can create observables from asynchronous sources. So this one pushes events in an imperative way, right? And it completes with an incomplete message. And on incomplete, we are signaling done. This is the end. And it returns a cancelable because all things in Monix are cancelable. So observable is, when we do subscribe, we can cancel a subscription in case we want to. So we can have hot observables, which are data sources that share their source. Observables usually are called, that's the default, meaning for each subscriber gets his very own data source. But you can share it. This is like memoization on task. You can share the data source to multiple subscribers. If you have a connection that's expensive, this is And you can turn a cold observable into a hot one at any point. In this example, this is a connectable observable. Nothing will happen until connect, but until we connect, we can subscribe multiple subscribers, ensuring that we have all the subscriptions that we need before starting the data source. This is also useful in practice, again, for expensive connections. We can do pooling, like we can turn a RESTful endpoint into a data source by repeatedly requesting data with concat map. This is flat map, but I'm naming it concat map because there's also merge map, which merges multiple data sources at once, and that's non-deterministic and unlawful. But this is flat map, and it has the properties of monad. We can also work with tasks, of course. And we can do filtering data in a pure way. Like we can describe a simple moving average that collects points. This is a stupid implementation. Our implementation is much more efficient. But to get the point, we collect data points and we calculate averages. And what happens is that we use scan, right? So scan takes points from the data source and evolves its state. Scan is the essence of functional reactive programming. Scan is all about state machines, right? You can say that I have a fetish for state machines. Sometimes at night I have nightmares with state machines transformed into push-down automatons. We can model like real state machines with scan. Like this is a small state machine that detects junk, so we can receive errors. We can receive signals that indicate errors in our power plants, but we don't want to react immediately because distributed systems, you can have junk on the wire. And so we want to wait to see that the signal repeats for 1 minute, let's say. If for 1 minute a failure signal repeats itself, that's when we declare fault. And we can model this, right, with a type state, which is either wait process. If we are in wait, then we wait. In process, we process. And we can model this with a pure data structure.
Did your talk have a cancelable?
Oh. Yeah, sorry. Okay. No, so it's cool. It can do throttling. I underestimated the length of my talk. Sorry. So the point is, Monix Observable handles decoupling, extreme decoupling, non-determinate, because it's the observer pattern. So it's all about the observer pattern. The observer pattern from the gang of 4, it's about decoupling, and observable is an observer on steroids, okay? It handles non-determinism, back pressure for free, and can be used in combination with actors, task, future. Yeah. I tried to integrate, integration with cats is in progress. I just wanted to say these are covered, right? These type classes are covered. Foldable and traverse, unfortunately, are not applicable because they are not asynchronous. They assume synchronous execution. And there are potentially missing type classes. I'm still trying to figure out which, like zippable, scannable, available, anyway. So, there isn't time for questions, right?
I think we have time for one question. If in the meantime the next
Yes.
speaker would prepare. And who has? Okay.
Daniel? Or?
I'm not sure who was first.
Oh,
Is Daniel first?
I can defer and ask later.
So very, very quickly, you said you implement both monad and applicative with your asynchronous primitives. Does that mean that your applicative is not consistent with monadic join? So in other words, does applicatives app2, your implementation, does that actually run things asynchronously, or is it actually consistent with the monadic flat map?
So flat map does ordering, applicative doesn't.
Okay, so when you compose two, I guess tasks together, observables together with app2, like it could run in either order. So it's not necessarily consistent with what would happen if you did it through flatmap.
Yes. So the applicative operation is called zip, and it's not equivalent to a flat map followed by a map. Yes.
Okay, thank you.
Oh, you're talking about AP. That's, yeah. Yeah. But by the way, I proved the laws. I mean, I'm integrating discipline and the cat's laws. Those projects are great. So, of course, yeah.
So first of all, thank you for Monix. We actually use it in Scala exercises on the client side. We use the task from Monix. And I just wanted to ask you, like, it looks like you rolled your own kind of state machinery.
Mm-hmm.
Why didn't you use the one provided by Akka? Is there a reason, like performance or?
Oh, the state machine in Akka, don't go there.
Okay. Cool.